Okay, so today we're going to talk about Unit 7.3, which is going to be our trigonometric functions, our integrals of trigonometric functions. Okay, so a little bit of recap, a little bit going backwards kind of to come forward. So let's talk about our derivatives. So the derivative of cosine x is negative sine x. So then the integral of positive sine x must be the opposite, which is going to be my cosine, but where does that negative go? It actually comes to the front, so it becomes the integral of sine x is going to be negative cosine x plus c. The derivative of sine x equals cosine x, so the integral of cosine x must equal sine x plus c. The derivative of tangent x is secant squared x, so the integral of secant squared x must be tan x plus c. You guys kind of see that pattern coming. All right, so the derivative of secant x is secant x tan x, so the integral of secant x tan x must be secant x plus c. Two more, the derivative of cotangent x is negative cosecant squared x, so the integral of cosecant squared x would just be negative cotangent x plus c. And finally, the derivative of cosecant x is negative cosecant cotangent x, so the integral of cosecant cotangent x would be negative cosecant x plus c. Okay, so let's actually evaluate a couple of these indefinite integrals using our trig. So the first one is the integral of 2 sine of x. So that's a pretty simple question, because what we're going to do is we're going to take out that constant multiple and then we're going to integrate. So I would have 2 times the indefinite integral of sine x dx. Well, I know this indefinite integral of sine x. I know the integral of sine x is negative cosine x. So this becomes 2 times negative cosine x plus c. And if I distribute that 2 in those negatives, it becomes negative 2 cosine x plus c. My next question is the integral of the entire quantity of pi secant squared theta minus cosecant squared theta. So here we have an option. We can take out our constant multiple. We can also do the sum and difference where we separate it. I like to do this because when we get to more complicated problems, it becomes easier when we take out the constant multiple, and when we do our sum and difference, it becomes visually more bite-sized, more manageable. So I'm going to go ahead and rewrite this. So this is going to become the pi times the integral of secant squared theta d theta. So it's this first half, and then minus the integral of cosecant squared theta d theta. Now we can look at these as little individual bite-sized pieces. So the integral of secant squared theta is tan, so it gives me pi times tan theta minus the integral of cosecant squared theta is actually negative cotangent x. So if I subtract a negative, it's just going to make it positive. So this becomes positive cotangent theta plus c. Can't forget that plus c. If I want to double check my work, there it is, pi tan theta plus cotangent theta. Went a little far. Here's our next problem. We're going to do the integral of the quantity 1 minus cosecant t cotangent t. And this should be dt. There's a little typo on my screen. My variable should match the variable on the inside because I'm deriving with respect to this variable. Otherwise, that's our differentiation, kind of like implicit differentiation with derivatives. Now, a common problem I see with this question is that kids want to treat this as a constant multiple. But what's that word? Constant multiple. 1 is not multiplying by anything like pi is multiplying by secant squared. 1 is not attached to anything. So this is my sum and difference rule, so I can split it apart. So this becomes the integral of 1, dt, minus the integral of cosecant t cotangent t dt. So now it's bite-sized chunks. I know that the integral of any constant value is just going to tack on that variable. So the integral of 1 must just be my variable t. So this becomes t minus the integral of cosecant cotangent is just negative cosecant. So it's going to be plus cosecant t plus c. If I want to double check my work, that is sort of correct. I've got some funky variables going on in my PowerPoint. If this were more correct, this would have been t, and this would have been t. Okay, My apologies, shouldn't look like that. Our next question is another one we can simply sum and difference, we can pull apart. But let's say I just wanted to attack this without pulling it apart. Well, what would I do? I would just take it step by step. So what is the, this is a constant multiple, so I'm just gonna bring my 2 down. So this becomes 2. And then my derivative of sine x is negative cosine. So I'm gonna bring my negative to the outside, cosine x. And then bring my plus down, bring my 3 down. The derivative of cosine x is sine x. And then what do we tack on to every indefinite integral? Plus c. So I wanted to double check that work right here, negative 2 cosine x plus 3 sine x plus c. And our final problem, didn't really give myself much room for it, but it's the derivative of secant y times the quantity tan y minus secant y. Well, the way it is right now, I can't integrate this. We haven't learned anything that teaches me what to do with this multiplication. So what I'm going to do is a little bit of algebra. We're going to distribute our secant y throughout. So I'm just going to rewrite this equation right here. So instead of secant y tan y, this is going to be secant y times this quantity. It's going to be secant y tan y minus secant times secant is secant squared dy. So this is my new integral. And again, we could just take it piece by piece. So what is the integral of secant tan? Well, that's just secant. So this becomes secant y. I bring my minus over. What is the integral of secant squared? Tan. This becomes secant y minus tangent y. Well, we tack on to every indefinite integral plus c. Okay, so all I did was algebra and a little bit of calculus. So if I want to double check my work, there's an answer right there, secant y minus tan y plus c. We did the correct job. Okay, so far we've been talking about indefinite integrals, but what happens with our trig when we have a definite integral? Well, not much changes. We still do these same steps. I integrate, maybe a little bit of algebra manipulation, but this time all we're going to do is add on that evaluation step, which we talked about in the fundamental theorem of calculus. So what we're just going to do is evaluate our integrals from f of b minus f of a. That's simple. So our first one is going to be the integral of sine x from pi over 2 to 3 pi over 2. So the first thing I'm going to do is integrate it. What is the integral of sine x? Well, it is negative cosine x. And then here, because it's a definite integral, we're not going to tack on plus c because we're actually evaluating it for a value. So we're going to evaluate it from pi over 2 to 3 pi over 2. And this is going to equal my f of b minus f of a, right? So my f of b is going to be f of 3 pi over 2. So this becomes negative cosine of 3 pi over 2 minus negative cosine of pi over 2. Well, the cosine of 3 pi over 2, so which quadrant am I in? I'm on my lines actually, from 0, pi over 2, pi, and 3 pi over 2, right? Thinking about our unit circle. If my cosine is down here, my cosine must be 0. So the cosine of 0 right here means I can cancel this out. And then guess what? 3 pi over 2, here's pi over 2, cosine is still 0, so my answer simply becomes 0. And if I want to double check my work, I have my answer right there. It is correct. Go us. Our next question involves secant squared. So again, we start with step 1. I'm going to integrate it. What is the integral of secant squared t? It would just be tan t. So this is going to become tangent t evaluated from 0 to pi over 4. This is going to be my fundamental theorem of calculus right here, f of b minus f of a. So I'm going to do, here's my f, tan of pi over 4 minus tan of 0. Well, the tan of pi over 4 is going to be square root of 2 over 2 over square root of 2 over 2, so something over itself is just 1. This is 1. And then the tangent of 0 is going to be 0 divided by 1, so it's just 0. So of course 1 minus 0 just gives me 1. If I want to double check that work, there it is. Ta-da, got the correct answer. So here's my next question. We've got the definite integral from 0 to pi over 4 of secant tan theta. So let's do that problem. What is the integral of secant tan? Just secant. So we have secant theta evaluated from 0 to pi over 4 equals my fundamental theorem, f of b minus f of a. So this becomes secant of pi over 4 minus secant of 0. Well, this is a little bit of trig to evaluate this. There's multiple ways to evaluate, but to evaluate this, I'm going to use the reciprocal. So my reciprocal of secant is cosine. So we're actually saying 1 over cosine of pi over 4 minus 1 over cosine of 0. Cosine of 0 is 1. So this cancels out, it's just left with 1. And the cosine of pi over 4 is square root of 2 over 2, but we're on the bottom, so I gotta flip it. So, I mean, you could have solved it. You could have just known that secant value at pi over 4. You could have known in your head it was gonna be the reciprocal of cosine. However you wanna solve it, there's multiple ways. So this actually becomes the 2 over the square root of 2 minus 1. Okay, if I want to double check that work, there's that answer. It is the correct answer. Regarding this answer, there on an AP test, especially a multiple choice test, it's very possible that they could have rewritten this answer. You might have a rationalized fraction instead with no radical on bottom. They might combine, have no fraction in general, just have have no quotient right here. No difference right here, just the fraction. My apologies. So there's multiple ways we can rewrite this, so that's something to just keep in mind if you're taking a multiple choice test. Our next question is going to be the integral of pi over 6 to pi over 3 cosecant x cotangent x. There's a little typo on your packet that says cosine right now, which we don't know how to do the integral of cosine times cotangent. We could do the integral of cosecant cotangent, so just make that little change in your packet. So what is the integral of cosecant cotangent? It's just negative cosecant, so this becomes negative cosecant x integrated from pi over 6 to pi over 3, which equals negative cosecant of pi over 3 minus negative cosecant pi over 6. Cosecant is the reciprocal of sine. So this becomes negative 1 over sine of pi over 3 plus 1 over sine of pi over 6. Sine of pi over 3 is the sine of 60 degrees, and that's the square root of 3 over 2, but we're on bottom, so we're going to flip it. So this becomes negative 2 over the square root of 3. The sine of pi over 6 is a sine of 30 degrees, which is 1/2. Again, we're on bottom, so we flip it. The reciprocal of 1/2 is just 2, so plus 2. So we have negative 2 over the square root of 3 plus 2, again, or 2 minus square root of 2 over square root of 3. Again, we can rationalize, get rid of this plus and combine. There's a lot of ways we can rewrite that. Our final question, it's a little hard to see, but it's the definite integral, or definite integral of pi over 6 to pi over 2 of cosecant squared y. So what is the integral of cosecant squared? It is a negative cotangent x, so it becomes negative cotangent, y, evaluated from pi over 6 to pi over 2. So this equals negative cotangent of pi over 2 minus a negative, so plus cotangent of pi over 6. Well, the cotangent of pi over 2 is 0 because tangent of pi over 2 is undefined, so if I flip that, so this becomes 0, I don't have to worry about this. The cotangent of pi over 6, so if we think about our pi over 6 is at 30 degrees in our quadrant, and you have a coordinate point of square root of 3 over 2, comma 1/2. Well, how do we see cotangent? We can see cotangent a few ways. We could see cotangent as 1 over tan, or we could see cotangent as cosine over sine. So we could see it as cosine over sine, right? So the square root of 3 over 2 divided by 1/2 is the same as saying multiplying by 2 over 1. So I'm going to get rid of those 2's, and the only answer I'm left with is the square root of 3. Let's double check. The answer is correct. It absolutely is. It says square root of 3. So good job. And that's it for trig integrals. It's really kind of a short chapter. It's pretty easy in nature. I think the hardest part is going to be just applying your unit circle, just kind of having to dig back in there and remember. Thank you.